All right. We just covered the counters just a little using T flip-flops. Let's do a little bit more comprehensive counter, and this time we are not limiting ourselves to T flip-flops. This is the counter I want to have, and then I will define certain terminologies here. Some of it we have already seen, the carry in, the carry out, and all that. So this is the counter. It has a carry in and it has a carry out. Carry in is for carry and carry out are for cascading, so that the same way a certain bit has a carry in and then also as a carry out, so you can put these bits together, these slices together, like what we did before. Okay, what we did here. See, this is actually carry in, this is carry out. So this slice connects to the next slide by carrying to the next slice by carrying carry out. Okay, well, if you look at the whole thing, again, you have a carry in on this side, you have a carry out on this side. So instead of putting one together, you can put four together. And therefore, what we have here is the carry in, carry out for this counter. Okay, so that's part of the terminology. So from this point on, anytime you hear carry in, carry out for the counter, that means those are the bits that you use for cascading. If you're not cascading a 4-bit counter, you're happy with the 4-bit counter, keep it as is. Just put a 1 on carry in if you want to enable it all the time, and then just leave the carry out open, but then when the count reaches 1111, that becomes 1. So you have a extra feature in this counter. So we learned carry in and carry out. We have already learned the clock and reset. Okay, so let me just mark this. This is for cascading or extra feature. Okay. I have clock and reset. Okay, no need to say anything about clock and reset. Those are given. Okay, I always have those. And I also have the output. The output is fine, and this is the output of the counter, the 4-bit output of the counter, which I call parallel output. Okay, that means the counter 4 bits. These are parallel altogether. 4 bits are providing the output. That's the count output: C0, C1, C2, C3. Okay, the reason we call this parallel output because this counter also has what is called a parallel input. Okay, this parallel input other than this unit that you are seeing here, other than it counting up from 5 to 6 to 7 to 8 to whatever, okay, other than this, anytime you decide that you don't want to count, you just want to load it with one data, let's say you load it with 11, and then you like your counter to go up from 11. Okay, so you do have this feature, the parallel load feature, the parallel inputs that can be loaded into the counter. Okay, remember with the other two counters I showed, we didn't have that feature. It's not a very sophisticated feature, but it's a very important one. It is not complex for implementation. You will see how it's implemented. But then having parallel input is a good thing to have with counters. And then we will see that we will have with other components as well. When I have parallel load, I have to have a way of controlling it. For parallel loading, I have an input called load that when that becomes 1 and clock arrives, parallel load is loaded into the register or into the counter. If load is not 1, then only then you can probably count. Probably because counting requires other conditions, which I'm going to talk about in a few minutes. So I have this, let me erase this. So the parallel input and the load, they work hand in hand. And the parallel input with the load is what goes into the output. Then we have, as it should be, the count feature of this thing. The count feature requires, first of all, load to be 0, count. Load is 0, that means you are not doing parallel loading. Carry in is 1, okay? Because if this is the right moles, the carry in is 1. If this is cascaded, we will see the cascading. The carry in is connected to the carry out of the other. Well, we will talk about that. And count is also 1. What it means is that I'm not in the load mode. Load mode is 0. I am in the count mode. But then when you are in the count mode, you can only count if carrying is 1. So in a way, carrying and the count mode, both of them have to be 1 for the counter to count up. All right. We will see the difference between the count and carry in when we are cascading these things together. So I have the parallel input that works with load and the parallel input, and then I have the let's say count or up count mode, which works with these 3 signals I am showing. And therefore, when I am in the up count mode, and these 3 signals are as they are, then I am doing up counting. So, have I said everything about this? Yes, I have. The function of the load, the function of carrying, the function of count, the function of carry out, the function of the clock and reset. We don't need to say anything about that. They are always there. Okay? Unquestionable part of my sequential hardware. And parallel input, since I have the capability of loading it with something, I have this parallel input. Okay, this is an up counter with parallel load capability and carry in, carry out. How do we build it? Well, this is just explaining that when the parallel output reaches 1, 1, 1, 1, the carry out becomes 1. And even if you do parallel loading, and you load 1, 1, 1, 1 into it, okay, if carrying is 1 and you have just loaded 1, 1, 1, 1 into it, carry out becomes 1 also. Provided the count mode becomes 1. All right. Anyway, how do we build this? Easy. Okay. I take 4 flip-flops. See what I have. I have 4 flip-flops. The clocks are tied together. I'm not showing the clocks are tied together because it gets it a little... let me do it with light yellow. The resets are tied together. Let me do that also with light yellow so that we don't make these diagrams so busy. Reset. Okay? We don't really talk about those. Those are all connected. So I have 4 flip-flops, and the inputs of the 4 flip-flops are coming from a logic which I call it incremental. It's not exactly incremental only, but then this circuit, this incrementer circuit, if load is 1, I'm going to do this. If load is 1, there is a multiplexer there that puts P3, P2, P1, P0. These are the parallel inputs on the D inputs of the flip-flops. These are the D inputs of the flip-flop, 1D. It's written a little bit up there, but that's it. Okay, so if load is 1, see the red lines, the parallel inputs go on the inputs. If load is 0, let's look at the next scenario. If load is 0, what color to use to make it very distinguishable from the other one? If load is 0, count is 1, carry in is 1. Okay, they go into the incrementer. The incrementer actually increments. So what happens is, in this mode here, these 4 parallel come together, get added to 1, and then these now go on the inputs of the 4 flip-flops. Okay, and therefore my incrementer is performing a +1 function. So I'm either doing the red, okay, which is the situation that load is 1. The parallel load just goes in there, ignores the incrementing and everything, just goes in there, loads the whatever I have on the parallel load input into the flip-flops. Okay, just like 4 independent flip-flops. But then if load is 0, carry in is 1, count is 1, then this incremental logic just takes the 4 inputs, adds a 1 to it, and then it puts those on the inputs of the flip-flop. What it means, if in this case, if I have 1101, which is 13, I clock it, it becomes 14. I clock it, becomes 15. Once it reaches 15, carry out becomes 1. And once it reaches 15, carry out becomes 1. You give it another clock. 1111 goes back to 0000. This is how this hardware works. And for cascading purposes, you also have a carry out. Carry out takes carry in and the count mode. That means if you are counting, and if you are your carry in is 1. Remember the AND gate? I put in one of those earlier counters that ANDs the carry in and the enable together. This is the kind of thing we are doing here. And this is carry out, which I will show you how we can use that for cascading. This is all there is to this, and now let's look a little bit more into the actual hardware of this. Okay, the actual hardware of it isn't all that surprising either. If load is 1, okay, I am taking the left input of the multiplexers, okay, If load is 0, which I think I used this color, and count is 1, and carry in is 1. See, count and carry in is 1, so I have a 1 on the input of the half adder. Remember the half adder. Half adders, they take 2 bits, they create a sum, and they create this carry. And then the carry of 1 goes into the input of the other one, and therefore a 1 on the very first one causes everything to count up 1 position. Okay, to add a 1 to it. And in this position, load is 0, so this is a 0 here. We are selecting the right input of the multiplexer, which goes into the inputs, and therefore if it's 0, these 4 go in, okay, get incremented on the output. Same with this one. Same with this one. And this one. Okay. And then clock arrives. So what happens is, goes here, it goes here. Goes here, it goes here. Okay. Clock arrives. The incremented value gets clocked into the 4 flip-flops. In case of load, though, in case of load, the half adders are ignored. This goes in here. This goes in here. This goes in here. And this goes in here. Clock arrives. These red lines get clocked into the 4 flip-flops. And I guess that clearly shows the hardware. If you have forgotten and you want to know what these half adders look inside, this is the output. This is this input, and this is the carry output. Okay, this is a half adder. Okay. So you put this in place of these half adders, and something I like you to see. Compare the add mode of this counter with this counter. Okay? Remember when I said that you can have T flip-flops, you can build T flip-flops out of D flip-flops. Okay? So if this is a D flip-flop, now what you have is T flip-flop. You just add an XOR. Look at the AND, the yellow AND here, and the XOR that I'm putting up there. Right? And the yellow XOR that I'm putting up there. Actually, this circuit is not very different than this circuit, considering the half adders only, not considering the parallel inputs, because that AND is this AND, that XOR is this XOR. See how the ands go from one half adder to the next, to the next, to the next, right? See, because this and output goes on this, and then it goes into the next and the same exact thing over there. Okay? Just wanted this observation. So I want you to look inside the gating and see the two counters building with D flip-flops and the building with the T are not that different. All right, what do we have now? We have this counter built in two different fashions. Now let's do cascading of these counters. Okay? Cascading of these counters works like this. I start with 0, 0, 0, 0 on the left counter, 0, 0, 0, 0 on the right counter. While the right counter is counting from 0, 0, 0, 0 to 1, 1, 1, 1, the left is quiet. Quiet, quiet. So this goes to 0, 0, 1. This goes to 0, 0, 1, 0. This is quiet. Sitting 0, 0, 0, 0. This continues until this gets to 1, 1, 1, 1. This is still quiet though. But then, when it reaches this count, the left counter notices that it has to be counting with the next clock. And therefore, it wakes up. It wakes up with the clock. And therefore, what happens is the next count takes the rightmost, rolls over back to 0, 0, 0, 0. But then the left count, that was the right count. The left count goes from 0, 0, 0, 0 to 0, 0, 0, 1. What it means is just woke up, counted one position, and then what happens? Dormant again until the next time this reaches 1, 1, 1, 1. Then this is still 0, 0, 0, 1. But then after that, this becomes 0, 0, 0, 0. This becomes 0, 0, 1, 0. Okay? How can I do this with these two counters here? Remember the carryout? The carryout is there so that when the counter reaches 1, 1, 1, 1, the carryout becomes 1. Okay? What did I say? I said when the counter becomes 1, 1, 1, 1, the left one wakes up and on the clock it counts up. So let's do this. Let's take this is the least, this is the most. Let's take the carry out of the least significant 4 bits and put that into the carrying of the most significant 4 bits. What do I do with the carrying of the right one? I just put a 1 on it. Okay? What do I do with the clock and reset? With the clock and reset, this is what I do, which I usually do. I connect the two together. Not the clock and reset, the clock and reset of the two together. Okay? Without usually even talking about it. The final carry, that is if you decide that you want to have another counter to the left-hand side, the final carry now comes from this. I make it slightly different color. If you want to use it for final carry or you want to use it for next cascading, it's up to you. Okay? And what do I do with the rest? Well, I had only 4 parallel inputs. Now I have 0, 1, 2, 3, 4, 5, 6, 7 8 parallel inputs and 4, 5, 6, 7, 8 parallel outputs. The same way I connected the clock and reset, I have to connect the load input of the two together. And the count is count enable. The count is count enable. Okay? Which means that if count enable is 1, you clock it, provided your carry in is 1 and provided load is 0, you count up. If load is 1, then you will do parallel loading, which we showed in red in the diagrams before. So if load is 1, this goes here, these 4, these 4. That's if load is 1. If load is not 1 and carry in is 1 and count is 1, then the only thing you do is just do count up, which is taking advantage of those full adders. All right, so we done good work with counters. We haven't shown you the Verilog description, but we will. Next topic is registers and the Verilog description.